Hello, everybody, and welcome to another wonderful day of chemistry. So last time we introduced the idea of how we can talk about concentrations of species using molarity. However, one of the things that's important to realize, and we've already seen this a little bit, that molarity is far from the only way we can talk about the concentration of a chemical solution. There are many different ways we can talk about concentrations. And there's essentially six major ones we'll be talking about today. And one of the things I want to talk about is not just what all of these concentrations are, as we've seen most of these already, but also the advantages of each and every one of them. Because when you're talking about concentrations, there's going to be advantage of each of these techniques. And thus it turns out that in class, we're going to spend a lot of time on how to convert in between these two, which will mostly come down to unit analysis. And again, each one will have situations where they're better and situations when they're worse. And that's an important thing to realize. So one of the first ones, and this is what we talked about last time, is molarity. Moles over liters. Incredibly useful, and this is going to be really important for chemical reactivities, as chemical reactivities all depend upon the amount of moles of any given solute in a solution. So I need to know how many moles of everything is present in solution, and I'm usually going to measure out my solutions in volume or in liters. So this is going to be very useful in the everyday kind of reaction chemistry, but we run into a slight problem. And then it turns out that volume is going to be temperature dependent. If I heat a solution of water, it turns out to become less dense, the volume increases, and so did my molarity. Oops, slightly problematic. And so again, our solutions will expand in volume in general, so concentration decreases with temperature. That can be kind of problematic if, you mix up a solution at room temperature and then you heat it to boiling, because Lord knows what your molarity is now. And another important feature is that it really depends on having a clear solute and a clear solvent. So you need to know who's being added to whom. And that can be a little bit tricky, especially if you have a solution that's kind of 50-50. It's a true mixture. And so as a result, molarity is mostly used by chemists because we're mixing things by given volumes and we care about how many moles of each thing is present. So that means if you leave chemistry, nobody's going to refer to things in molarity. That means if you need to do chemistry on a known solution you buy off of the shelf, you're going to need to figure out how to convert one of the other types of concentrations into molarity. Now, almost as good for chemists is mole fraction. So this is really just the ratio of the moles of the thing I care about, usually my solute, versus the sum of all of the moles of all components. So this is actually a really useful metric, as we now have no temperature dependence because moles won't change with temperature. And it's not limited to liquids. It can be to any sort of mixture of solids, liquids, gases, all of the above. Two solids mixed together, two gases mixed together, doesn't really matter. So this is actually a really useful thing. It also, again, doesn't have a clear reference to who's the solution, who's the solvent, and who's the solute. So this also makes it a lot more general and flexible. The problem is if I ask you to prep a solution, I don't say you give me 20 moles of this given mixture. That's kind of annoying, which means that inevitably, while you can use this for a lot of calculations, you're typically not going to have something labeled as a 0.2 mole fraction solution. So really what ends up happening is that usually you're going to be given something in percent weights and determine the mole fraction from that percent weight. And we already saw how to do that at the beginning of the chapter of converting in between percent weights and mole fractions and back and forth. And this can be really useful. And that gets us to percent weights. So the idea of percent weight is pretty analogous to mole fraction. It's the mass of the thing I care about, usually my solute, divided by the mass of everything all together. And this actually is a really easy thing to mix, because oftentimes when you're mixing things, especially let's say you're cooking in Europe, you'll notice that all the recipes that come from Europe have everything listed in mass. It's very steady, doesn't change with temperatures or pressures. It's nice even. works really well, fairly easy to do. And it doesn't require any sort of conversions. However, if we're going to make use of percent weights when doing reactions, we have to figure out how to convert percent weights into things like mole fractions or molarities, which can be a little bit tricky. Also, one of the things that you should really watch out with percent weights is a lot of times people will label a percent weight simply by giving the sign percent. But you should watch out because some of the lesser used concentration units are percent volume. So volume of solute over total volume, or mole percent, or here's a fun one, the mass of a solute over the volume of the solution. And you can find all of these used in the real world. Just go down your average average cosmetic or cleaning aisle, and you'll find all three of those. And it can be kind of tricky. Not to mention, one of the things we often have to watch out for is a lot of solutions will have a very low concentration, whether we're looking at weight percent or mole fraction. So frequently, you're going to have these very low concentrations reported as parts per million. So this is especially common with environmental contaminants, as a very small amount can lead to a big problem. So one of the most typical of these parts per notation is going to be parts per million. And this is most commonly referred to as the mass of the solute divided by the mass of the total solution. So in this case, you're going to take this mass ratio and then divide by 1,000,000. And it turns out that this will be the same thing as 1 gram of solute per 1,000,000 grams of solution, which with some clever unit analysis, you'll find is the same thing as milligrams per kilogram. So if you see a ppm in mass units, milligrams per kilogram, same thing. However, one of the other things that is worth noting is if you have a dilute aqueous solution, you can usually treat the density of water as 1 gram per milliliter or 1 kilogram per liter. Under that case, and again, only for aqueous solutions, you can approximate parts per million as milligrams per liter. And again, this should work fairly well. However, if you've got a really dilute system, you can replace parts per million with parts per billion, or for a very dilute system, parts per trillion. However, one of the most lesser used ones is going to be parts per 1,000. So mass of solute divided by mass of solution times 1,000. Same thing as grams per kilogram. Mass of parts per billion would be mass over mass times 10 to the 9th. So this is the same as micrograms of whatever we care about over kilograms of solution, or for aqueous system, micrograms per liter. Parts per trillion, this one's a little bit less common. This would be nanograms of a solute per liter. So again, very small amounts. But it turns out if you're dealing with things like lead contaminant, parts per trillion can be enough to cause an issue. So one of the biggest things I want you to be aware of in any of the parts per notation is that it's often used very sloppily. So for example, somebody may say parts per million, and what they're actually referring to is not mass per mass, but moles per mole. So the moles of a solute per total number of moles. Again, times 1,000,000. Or it could be moles per liter, which would be more or less molarity times 1,000,000. Or it could be a percent volume, but instead of times 100, it's times 1,000,000. And this would also count. And this is slightly problematic. And one of the things I want you to be very clear of, if you see a notation in the real world that's parts per 1,000, parts per million, parts per billion, parts per trillion, always double check whether it's mass per mass, moles per mole, volume per volume, or some sort of mixture, because this can make a big difference when you're talking about the real significance of those numbers. Now, there's one last important unit of concentration we should be aware of. And this one's kind of a chemistry special. And this is called molality. Not to be confused with molarity, where this is moles of solute per kilograms of solvent. So this one's actually fairly frequently used in industry because it's actually fairly easy to prepare. You often know the moles of your solute. You can determine this by the mass of that. And then instead of knowing the final volume of your solution, you just add a known mass of solvent. So if I'm, for example, preparing a Molal solution, I may add, say, 1 mole of sodium chloride and then add in 3 kilograms of solvent. And there you go. That will give me an easy molality. And it also has a big advantage that it has no temperature dependence, because moles and kilograms will not depend on temperature. And the mass of solvent really isn't going to change in the course of a chemical reaction, unlike the volume of a system. But it is worth noting, this is going to be most commonly used in physics, chemical industry, and engineering. Things where it's very easy to measure masses, and you're not going to be paying as close attention to volumes. So this gives us an idea of all the various types of concentration we can use. Next time, we're going to be looking at how we can change concentrations by looking at dilution. Next time, we'll see you with M1V1, M2V2. Till then, take care.